Welcome to Calculus, section 4.2. I'm going to work an example, one that we could do solve with geometry, but we're going to kind of prove or confirm that the calculus is actually working to find the area under a curve. And I think I'll try to get two examples in. They might need to be split into two videos, but the formula we're going to use, which we talked about a little bit in class, is that the area under the curve is the limit as n approaches infinity, where n is the number of rectangles, so you want to have it those to approach infinity for I equaling 1 to n. So that's going to be rectangle 1, rectangle 2, rectangle 3, rectangle 4. And then the area of a rectangle would be you could say the width times the height. The width we're going to represent by delta x, and the height by f. The function, which will be evaluated at varying places, and we're going to say ci. So that's an I right here, by the way. Let's see. This is an I. So this ci here represents the height. Okay. And what do all those things stand for? Well, delta x, as we've heard before, is the width of each rectangle, which can be represented by b minus a, the distance between the upper and lower bound, divided by n, the number of rectangles. And ci, we're going to do this for assuming right endpoints. If you think about this, it does make a little bit of sense. It'll be at a plus I delta x. These formulas will be given to you. And let's think through why this ci thing makes sense really quick here. So if you have a curve like this is f at x and y, then if you were to find the area from here to here, you want to find this area. You're going to break it into some rectangles. Let's change it up here. You're going to break it into a rectangle like that. Like that. This is not really drawn that well. And like that. Well, the x coordinate here, this would be at A, this would be at B, and this one, I can't write this small, right here, would be A plus delta x, because you're going delta x over. This next one would be A plus 2 of those delta x things. And then you could use B, but not really knowing how long it's going to be, it just keeps going. 3 delta x's, 4 delta x's, depending on how many rectangles you have. So that's what's happening here. This is saying A plus delta x, some number of delta x's, I and I delta x's. If you notice, the summation is going to take it from 1 to 2 to 3 to 4. How many? It's going to do n rectangles. So the very first one is where that's 1, so it's starting you here. So it's starting with a right endpoint. Okay, a little bit of theory there. Let's do an example, and I'm going to find the area under a line. This is one, it's going to be a trapezoidal region. We could do this with geometry, and we will, but I'm going to do it with geometry and calculus just to confirm this process. Okay, so we're going to find the area. I'm not going to write that out, but find the area under f at x equals negative 3x plus 9 between, or in the region from 0 to 2. This is going to be a nice one. Okay, so I'm not going to rewrite that formula, but the first thing I do, the limit summation formula, is I find delta x. Delta x, as we said, is b minus a over n. In other words, delta x, and this one's going to be 2 over n. The other thing is ci. Ci is a plus I. Wow, that's a bad plus. Try to erase. Is, sorry about that. A plus I times delta x, which we said is 2 over n. So ci and delta x are often similar. It becomes ti over n. Okay, this certainly won't fit on a page, but let's begin. Why not? So the area is the limit as delta x approaches infinity, summation in I equals 1. Our delta x is 2 over n, and then times f at 2I over n. First thing I do, and if you've been in class with me, you know that I mentioned this, that these two things are like gatekeepers, the limit and the summation. You may not pass them if you have a variable that they are looking for. The first gatekeeper, the summation, is looking for the variable I, because everywhere he sees an I, he's going to plug in his 1, then 2, then 3, and so on. Delta x is looking for the variable, or the limit is looking for the variable delta x. That shouldn't be delta x. Sorry about that. Hopefully you didn't pause and try to figure that out. That should be n, right? N, the number of rectangles. We don't want the width to go to infinity. That would make no sense. So this limit is looking for n's. So if you have an n, you may not pass him. So the first one you can't pass if you have i's. Second one, n's. So this term here does not have i's. So actually I can pass him through, and this just makes it a little bit easier to work with. So I'm going to pull that 2 over n out front, and I'm left with this f at 2I over n. Well, let's go ahead and evaluate that. That's going to be negative 3 times, not x, but we're going to put everywhere there's an x, 2I over n. And this is going to work out pretty nice. I'm not having to do any quadratic or cubic stuff. So probably the last line we fit on this page. Let's see what we can do with this. I think I'm just going to do some simplifying here and rewrite this as negative 6I over n. You know what, let's get a common denominator. So what's... No, we don't need a common denominator. That's not right. So let's leave it like this, and the next step we're able to actually split this. And this is what I do. You don't have to do it this way, but I think it's really nice and concise and easy to follow. So we'll pick up on the next page. Okay, so the next thing I'm going to do is divvy that summation into two parts. Hopefully I wrote this down right. So I had the negative 6I over n. I'm going to pull out the negative 6 over n. So everything comes past it except the I. This goes from 1 to n. And then lastly we had the 9. And I don't do much with constants. We'll leave it in there. Okay, so this is where we go grab the formulas. You will be provided these formulas. Let's copy everything down. A lot of writing on these. Okay, so the formula for summation as I goes from 1 to n, and the rule is I would be simply n times n plus 1 over 2. And the summation as I goes from 1 to n of 9 is just 9n. Over here, you see some cancellations. That n cancels with that n. This 2 cancels with this and becomes a 3. I'm going to put the negative up here so I don't lose it. I'll get rid of that. Okay. Back to, so now we have area as the limit as n approaches infinity, 2 over n. Within here we now have, I'm going to distribute this here and here, negative 3n minus 3 plus 9n. Okay. So now I'm going to take this 2 just to get him out of there. This is a bit weird move, but I'm going to put 2 there. And I'm going to take the n and push it under. So I'm going to have 6n combining this term and this term, right? That was a 9. minus 3 over n. Now what should always happen when you get to this point is the degree in the numerator of what's left should equal the degree in the denominator, and that is the case here. You can see I have first degree here, first degree there. So as n approaches infinity, this is going to approach 6. But you do have that 2 out front, so we're going to have a equals 2. All this becomes 6, and that tells me my area is simply 12. So is that a good answer? It seems kind of too nice. Well, let's look on the next slide. Let's do this problem in kind of a more geometry process, and it'll take about 30 seconds. So what we were asked to do again was find the area under y equals negative 3x plus 9 from 0 to 2. Well, y equals negative 3x plus 9 looks like this. It goes through 9, has a slope of negative 3, so something like this. So that means it's going to hit here at 3. And to find that area, oh, did I say? Oh, yeah, that's right. We're only going to look, though, to find the area from 0 to 2. So the area is just going to be that chunk. Sorry, this is not the neatest. So we're only going to go there. So the region really you should see how nice the one on my paper is. Much better than this. It looks something like that. Where this is at 2, 3. This is at 0, 9. So that's just a trapezoid. The area of a trapezoid is you average the bases, that's how I memorize it, times the height. Well, the bases are, it's kind of sideways, but the bases are here, here, and that, I guess I should label this. This is at 2, 0, and this is at 0, 0. So that distance is 3. And that distance is 9. And the height in this case is the distance between the bases. That distance. And that is 2 to get from 0, 0 to 2, 0. So the 2's cancel, and you do indeed get 12. So certainly this would not be a good problem to do with calculus. We don't need it. But hopefully by seeing us do it both ways, you feel a little bit more confident. I'm going to do a hard one in another video. We won't have to do as much introduction, but it'll be a little more challenging. That might be a good supplement if you're having trouble with the tough ones. Thanks for tuning in. See you next time.